Okay, so let us look at a related topic to electronegativity, and that has to do with the polarity of bonds. Okay, so um, electronegativity, let's define that first. It's basically a measure of the ability of an atom to attract its shared electrons with another atom to itself. And it turns out that this electronegativity value is related to both ionization energy and electron affinity. And the greater the electronegativity of an atom in a molecule, then the more strongly that atom attracts the electrons that it shares in a covalent bond. And if you look at the trends in the periodic table with respect to electronegativity, you'll see that generally speaking, electronegativity increases from left to right of any period and from bottom to top of any group. All right, so that's a trend as far as that particular property is concerned. And this table was developed by a very important scientist, Linus Pauling. He basically did some theoretical work to come up with a scale for measuring the electronegativity of different elements. And the result of that scale, it's actually a 4-point scale where 4 is the highest possible electronegativity value. As you can see here, fluorine is that element. That's the most electronegative element. And basically, he did some theoretical work, as I said before, to end up with these numbers being assigned to the different elements, right? So this is what we're going to use for the most part in terms of comparing electronegativity values of different elements and predicting things like polarity and so on, as we're going to see later on. It's very important and probably a good idea for you to remember the four most electronegative elements are nitrogen, oxygen, fluorine, and chlorine. All right. So based on the relative positions of the elements in the periodic table, you should be able to answer this question or these questions. Basically, it's asking for you to arrange these elements in order of increasing electronegativity values. So in order for you to do this, you can consult your periodic table. In fact, that's what the question says, just refer to the periodic table only. So let's look at the first three elements given here. And based on their positions in the periodic table, I see that they're in the same period. So remember, going from left to right, the electronegativity increases within any period. So based on that fact, I would say that the least electronegative element is magnesium, followed by silicon, followed by chlorine. All right, so basically that's the order of electronegativity for those three. Now, in the case of these three, if you look at the periodic table in period, or I should say in group 5A, you'll see that these are the elements located in group 5A. And as we said before, the electronegativity increases going from bottom to top of that group. So in this group, the least electronegative element would be the antimony, which is SB. And then the one next in line would be arsenic, which is AS. And then the next in line would be nitrogen. All right. And then now for the final three here, this is a bit more complicated than the first two because what you'll find is that arsenic and selenium are in the same period, but arsenic and antimony are in the same group. So in this case, because antimony is arsenic in group 5A, then antimony would be the least electronegative element of these three, followed by arsenic. And then because selenium is to the right of arsenic in that period, which would be period 5, then we would put selenium as the most electronegative element of that particular series. Okay, so that's basically how this example is done. All right, now we're going to get into a discussion of polarity now. So a couple of things we want to talk about, different situations where atoms are bonded to each other. Now, if you have two identical atoms, right, which obviously mean they have the same electronegativity value, then what that means is that the bonding pairs of electrons that are shared between them, those pairs of electrons will be shared equally, and therefore we say that this bond is a nonpolar covalent bond, all right? On the other hand, if you have two different atoms where the electronegativity differ significantly, then the electron pairs will be shared unequally. And in such a situation, if you have the unequal sharing of electrons, even though the electrons are being shared, but it's uneven, then we say that that bond is a polar covalent bond. Now, you can have a situation where the electrons are so unevenly distributed that you basically have the transfer of electrons from one atom to the other. And the result will be the formation of ions, and therefore we end up with what is called an ionic bond. All right. So basically, those are the three fundamental types of bonds. Basically, you have covalent bonds and ionic bonds. But remember, when it comes to covalent bonds, you have two types. You have the nonpolar covalent bonds where the electrons are shared equally between the atoms involved, and then you have the polar covalent bond where the electrons are not shared equally. So those are the different types of bonds based on the electronegativity differences. And this diagram here basically gives you the different types of bonding in terms of different atoms connected to each other. Okay, where's my pointer? Okay, let me go here. Okay, so basically, for example, a carbon to hydrogen bond is basically non-polar, all right? And then you have the NH bond, which is a bit more polar. The carbon to oxygen bond is even more polar, and so on. And then you have the ionic bond starting from here, Na to S, Mg to N. And let me just say that, this is not a perfect system in terms of predicting whether or not a bond is polar. As it states here, there's no sharp cutoff point between, for example, ionic and covalent bonds. So you can have some overlap in terms of the different types of bonding. And then, of course, we have an extreme here where you have fluorine, which is the most electronegative element, and cesium, which is the least electronegative element. So therefore, that is basically the widest difference in terms of electronegativity you can have. And therefore, the bond formed between these two atoms is considered to be ionic. Now, different people use different criteria for determining whether or not a bond is polar covalent, non-polar covalent, or ionic. So what I'm going to discuss here is one particular criteria that is used, or a set of criteria that is used to put the different bonds in their separate categories. So we're going to start off with a discussion of the non-polar covalent bond in more detail. As we said before, in such a bond, you have basically equal sharing or almost equal sharing of electrons between atoms involved in that type of bonding. And this type of bonding typically occurs between nonmetals, all right? Now, the criteria that we will use for determining whether or not a bond is nonpolar covalent is if the electronegativity difference is between 0.0 to 0.4. And these are just three examples here. So any situation where you have two atoms identically bonded to each other, that would be essentially a nonpolar covalent bond because the difference in electronegativity would be zero because they're both the same. In the case of the chlorine to bromine bond, the difference in their electronegativity is 0.2, which is within the 0.0 to 0.4 range, and therefore, again, that bond is nonpolar, all right? And then the last example here, the hydrogen to silicon bond, again, that is essentially nonpolar based on the difference being equal to, the difference in electronegativity being equal to 0.3, which again lies between the 0.0 to 0.4 range. So that's how we, using this criteria, that's how we can determine a nonpolar covalent bond. Then we get to the polar covalent bond. Now, again, this tends to occur between nonmetallic atoms, and the difference between that and, of course, the nonpolar covalent bonds is that the polar covalent bonds have unequal sharing of electrons. And the difference in electronegativity would range from 0.5 to 1.7. So these are the examples shown here. So if you take the oxygen to chlorine bond, the difference is 0.5 in terms of the electronegativity values. So therefore, that belongs to the polar covalent category. And you see similarly for the chlorine to carbon and the oxygen to sulfur, you see again that they both fall within the 0.5 to 1.7 range. All right. Then we get to the other extreme, ionic bonding. If the electronegativity difference is 1.8 or more, then basically between two atoms bonded to each other, then basically that bond is considered to be ionic. This typically occurs between metals and nonmetals, and basically it's a consequence of electron transfer from the metal to the non-metal. So if you take, for example, the potassium to chlorine bond, where the difference is 2.2, or the sodium to nitrogen bond, where the difference in electronegativity is 2.1, or the the sulfur to cesium bond, where the difference in electronegativity is 1.8. In all these cases, they're considered to be ionic because they fit into the range described here, or the criteria that we're using here to define what is an ionic bond. All right. Okay. So how do we depict using diagrams polar covalent bonds? Well, we can use this representation here. So just to give you some contrast, this is the hydrogen molecule. This is the hydrogen to chlorine molecule. And this is basically representing the even distribution of electrons between the two identical hydrogen atoms in the hydrogen molecule. In this case, however, where chlorine is more electronegative than hydrogen, in the hydrogen chloride molecule, you see that this represents an uneven distribution, which basically means that the electrons will be more attracted to the chlorine, and therefore you'll most likely find the shared electrons around the chlorine atom compared to the hydrogen atom. And then this picture here, it's called an electrostatic molecular diagram. Basically, it's used to give you a picture of what the distribution of the electrons are. The reddish region basically represents the negative end of the bond between the hydrogen and chlorine, and the blue represents the positive, right? So these are different ways of depicting polar covalent bonds. But you have some other ways as well. For example, you can represent the polarity of the bond using these symbols. Now, this is the Greek letter delta. So delta minus and delta plus basically represent partial negative and positive charges. So what this is saying is that you won't have a full negative charge on the chlorine. It's going to be a partial charge. And as a result of that, you'll have also a partial positive charge, not a full positive charge on the hydrogen. So basically, we can represent a polar bond using this representation as well. Another way of representing a polar bond is by using this symbolism here, which is, as you can see, an arrow with a cross at the tail. And this represents the direction of what we call the dipole moment, which we'll talk about later on. So basically, the arrow, to represent the direction of the polarity, the arrow conventionally is arranged such that it's pointing from the positive end of the molecule to the negative end. All right. So if you see this, then you should understand that where the arrow is, or I should say the head of the arrow, that's where the negative charge is, the partial negative charge that we discussed here, and the tail end of the arrow indicates where the positive charge of the polarity is located. Okay, so based on what we have discussed here, we should be able to answer this question. It says, use the electronegativity values to arrange the following bonds in order of increasing polarity. So I looked at this exercise before, and I calculated the difference in electronegativities of the two atoms involved in each case. And these are the values that I obtained. So in the case of the bromine to chlorine bond, the difference in electronegativity is 0.2. In the case of the chlorine to chlorine bond, that is obviously 0 because the two atoms are identical. In the case of the chlorine to fluorine bond, that's 1.0. In the case of the hydrogen to chlorine bond, that's 0.9. And finally, in the case of the iodine to chlorine bond, that is 0.5. So I got these numbers by simply using the values for the electronegativity of the different atoms and finding the difference between the two atoms involved in each case. So therefore, based on these numbers, we can arrange these bonds in terms of increasing polarity. So the answer would be that the chlorine to chlorine bond would be the least polar, followed by the bromine to chlorine bond, followed by the iodine to chlorine bond, followed by the hydrogen to chlorine bond, followed by the chlorine to fluorine bond. And that would be the answer. Okay, all right, so that's it for this video. So The next video we'll be talking about the concept of resonance.